Welcome to ASU's University Academic Success Programs. This video will cover the topic capacitors.
I've actually been wondering, what is a capacitor?
I'm glad you asked. A capacitor is an electrical component with two terminals that stores electrical energy in an electric field. They can be made many different ways, but they usually contain at least two electrical conductors, which are in the form of metal plates. An energy source, like a battery, will charge a capacitor, and if the battery is removed, the capacitor will dissipate the energy stored inside it. For example, think of a rechargeable battery inside a cell phone. This battery is like a capacitor. An energy source charges it, and then when the source is removed, it dissipates its energy to power the cell phone. The effect of a capacitor is called capacitance, and it can be written as charge over voltage. So to find the capacitance of a capacitor, if we have the charge across the capacitor and the voltage across the capacitor, we divide the charge by the voltage. We could say the unit for capacitance is coulombs per volts. But there is a unit for capacitance, farads. Another known formula for capacitance is C equals A times epsilon naught divided by D, where A is the surface area of the capacitor plate in meters squared. Epsilon naught is the permittivity constant, which is 8.85 times 10 to the negative 12th coulombs squared over Newton meters squared. And D is the distance in meters between the two electrodes of the capacitor.
Okay, I understand now. What else can we learn about capacitors?
Let's discuss capacitors in circuits. Here is a basic circuit with a capacitor. If given the voltage V of the source and the capacitance C of the capacitor, we could use the formula to solve for the charge.
What happens if there are multiple capacitors in the circuit?
Good question. Let's say we have three capacitors in parallel. For a quick review, parallel, as seen here, means that components are attached together on the tops and bottoms. So C1, C2, and C3 are in parallel with each other because they are attached on their tops and on the bottoms. Let's say that the first capacitor, C1, has a capacitance of 6 microfarads. C2 has a capacitance of 2 microfarads. And C3 has a capacitance of 3 microfarads. Before we can use the capacitance relationship with the voltage source, we have to first combine the capacitors to get one total capacitance. When the capacitors are in parallel, the rule is we add them together. So from this rule, what is the total capacitance of this circuit?
So, we add them all together. 6 microfarad plus 2 microfarad plus 3 microfarad equals 11 microfarad, right?
Yes, you are correct. Now we will learn how to combine capacitors in series. Series is another structure of circuits. As shown here, series means that components are only attached on one side, back to back. So C1, C2, and C3 are now in series. To combine these capacitors in series, we find the inverse of the sum of the inverses of the individual capacitances. Here's what this formula looks like. C total equals 1 over C1 plus 1 over C2 plus 1 over C3. Now we will substitute the numbers in. 1 over 6 microfarads plus 1 over 2 microfarads plus 1 over 3 microfarads. And after performing this whole calculation, we find that C total equals 1 microfarad. This is how you combine capacitors in parallel and series. After you find the total capacitance, then you can relate it with the charge and voltage. Now let's learn about finding the energy stored in a capacitor. As charge is transferred across the plates of a capacitor, the potential energy of the capacitor increases. For a fully charged capacitor, there are three derived formulas for the stored energy. U, which is our energy in joules, equals Q squared over 2C, and it also equals CV squared over 2, and it also equals QV over 2. Where again, U is our energy in joules, Q is the charge in coulombs, as mentioned earlier, C is the capacitance in farads, also as mentioned earlier, and V is the voltage in volts, also as mentioned earlier. Because in these formulas we are talking about a fully charged capacitor, the voltage in these equations is the total voltage of the voltage source.
Can we do an example problem of finding energy in a capacitor?
Sure, here's a good problem. We have a parallel plate capacitor that has area equals 353 centimeters squared. The distance between the plates is 1.97 millimeters, and the voltage that is charging the capacitor is 575 volts. The problem asks us to find the energy U stored in the capacitor.
This one seems pretty challenging. Can we work through it step by step?
Yes, of course. This one is a little more tricky. Instead of directly giving the values needed to solve for the energy, it gives you some values you can use to find values needed for the energy. In this problem, we need to first find the capacitance of the capacitor. We will use the formula C equals A times epsilon naught over D. The area is given as 353 centimeters squared. We will need to convert this to meters squared so that our final calculation runs smoothly. This converts to 0.0353 meters squared. The distance between the two capacitor plates, D, at 1.97 millimeters, converts to 0.00197 meters. Now let's substitute these into the formula. C equals 0.0353 times 8.85 times 10 to the negative 12th divided by 0.00197. Because everything is converted into basic units, the answer will come out in farads. C equals 1.59 times 10 to the negative 10th farads. Now we would use this value with the given voltage in the formula U equals CV squared over 2. U equals 1.59 times 10 to the negative 10th times 575 squared divided by 2. And after making this calculation, we find U equals 2.62 times 10 to the negative 5th joules. This is the amount of energy stored in this capacitor.
Okay, I understand. So, sometimes we will be given problems in which we have to solve for something that we will then use to solve for the final answer.
Yes, and this helps us to review multiple topics in a single problem.
Thank you. What I'm understanding here is that capacitors deal with electric charge and voltage from a source. Using these values, we can solve for capacitance. And we can also solve for capacitance if we know the surface area of the capacitor and the distance between the two electrodes. If there are multiple capacitors in the circuit, then we have to use the methods described earlier to combine the capacitors before we can use them in the relationship. Charge, voltage, and capacitance can also be used to find the energy stored in a capacitor.
Great understanding. It looks like you're ready for some more practice with capacitors.